Hello everybody. This is going to be the first video in our acid-base chapter. We're going to start with some definitions, learn a little bit about acids and bases, and then we'll move on to some of the calculations that you can do in this chapter. So the properties of acids and bases. Acids are usually found in things like juices and fruits. They're usually really sour or tart tasting. They like to conduct electricity because they're made up of electrolytes. We can get that electricity to be conducted. They react with metals, and they're very often aqueous and liquid forms. Compare that to bases. Bases are usually cleaning products. A lot of the household cleaners that people use are bases. If you were to taste a base, it would be bitter tasting. A lot of bases are poisonous, toxic substances, and our body has developed over, however many millennia to be able to notice that as a bitter taste. They're also usually a slippery feeling. You don't really want to be touching the bases with your bare hands, but if you were, they would feel a little bit slippery. It's also very common for them to be in a solid form. Now, you usually learn that even in elementary school, middle school, but what you don't often learn is that there's different definitions of acids and bases. So what you typically learn is called the Arrhenius definition, which is the most simple version. There's kind of the middle of the road one, BronstedLowry, and then there's the most complicated definition, which are called Lewis. So Arrhenius acids make hydrogen ions when you dump them in water. You get H pluses floating around. And you get hydroxides floating around. That's what most people think of when they think of acids and bases. The problem is that doesn't really cover the more complicated examples. So the Bronsted-Lowry definition is a little bit more generic and it will cover more options. Acids donate protons, okay? Bases like to accept protons. The Arrhenius acids and bases meet these criteria. So all of the things you're used to thinking of acids and bases will still work under the Bronsted-Lowry definition. However, the Bronsted-Lowry definition doesn't cover some of the really weird acids and bases, the more complicated ones. For those, we need an even more generic example, which is called Lewis acids and bases. A Lewis acid accepts electron pairs from other things, whereas bases donate those electron pairs. People get these really mixed up. They have to keep track of 3 different definitions, things that could be one but not fit another. Sometimes things are being donated, but in the other definition, different things are being accepted. It gets a little hard to keep track of. There are not very many topics in chemistry where I suggest good old-fashioned flashcards. Acids and bases is one of those times where a good old-fashioned deck of flashcards, memorizing definitions, and memorizing some common examples may be helpful to you. So let's look at some examples. Our Arrhenius acids make hydrogen ions. Like this. This is an acid. Nitric acid loses the hydrogen, and now the hydrogen ion is floating around in our water. The bases make our hydroxides, something like this. Potassium hydroxide, dump that into water. The water disrupts that bond, the hydroxide goes floating around by itself. These are exactly what you're used to. These are very easy to spot. These are easy to recognize. I wish they all stayed easy to recognize, but they don't. Next, let's look at the Bronsted-Lowry. Acids donate protons, bases will accept them. Let's look at this little cartoon. This may actually be something you want to sketch because I feel like it is really helpful. The acid wants to get rid of this, wants to get rid of this hydrogen ion. A hydrogen ion is a proton, isn't it? The base is like, yeah, sure, I'll take that. That sounds great. So let's look at this example. Here, we are not going to end up with a hydrogen ion floating around by itself. Instead, it gets stuck onto the other chemical. Instead of NH3, I now have NH4. This chemical here was an acid. It wanted to donate the hydrogen, right? This right here was a base. It was happy to accept it. Now, instead of being NH3, it's NH4+. So I don't see a hydroxide floating around. I don't see a hydrogen ion by itself. But what I do see is one chemical donating a hydrogen to the other. This is going to cover more things than the Arrhenius model did. More chemicals are going to be considered acids and bases using this setup. Unfortunately, it still doesn't cover everything. There are some complicated ones where we need the Lewis definition. Acids accept electron pairs, bases donate electron pairs. So look at these Lewis structures for a minute. We have BF3 over here. Remember, boron is electron deficient. It doesn't have a full set of 8 here. And if you look here, this Lewis base has a lone pair. So what ends up happening is these two compounds end up stuck together. This one was the acid because it accepted the electrons. It was deficient, right? And now it accepted some extra. This one was the base. It had extra to donate. When it donates, it made this bond. These are the most complicated kind. This will cover everything, okay? The nice thing is we don't see very many Lewis acids and bases. My suggestion is always look to see if it's an Arrhenius one first. If not, then look to see if Bronsted-Lowry works. If not, then and only then look if it's a Lewis acid or base. I love this graphic. So this is kind of like that situation where all squares are rectangles, but not all rectangles are squares. Same thing here. All Arrhenius acids and bases are Bronsted-Lowry ones, but not all Bronsted-Lowry are Arrhenius. All Bronsted-Lowry are Lewis acid bases, but not all Lewis acid bases are Bronsted-Lowry. Arrhenius is the most specific, the narrowest definition, the fewest things count. Bronsted-Lowry is in the middle. Lewis is the most generic. I also like inside the circles the little generic examples they gave you. I would for sure write that down. Now, some things are always acids and some are always base. And then sometimes things can behave as either an acid or a base depending on the situation. Okay? Water is one of those times. Water can act as an acid or a base. We don't think of it as acidic. We don't think of it as basic, right? But it can behave that way based on the scenario that it's in. So let me show you what I mean by that. It's going to depend on what the other chemical present would like to do. Water is always going to be willing to do the opposite of what it's paired with. So for example, NH3 plus water makes NH4 plus our hydroxide. You're going to notice I like to write water as HOH. These are oftentimes going to be those double displacement reactions, and so I like to write it as an HOH. If you look, water is donating a proton, isn't it? So if water is donating a proton, is it an acid or a base? It's an acid. Over here, NH3 likes to be a base. So water says, okay, fine, you want to be a base, then I'm happy to be an acid. Compare that to this example. Well, this is hydrochloric acid. Water goes, okay, well, you want to be an acid, so I'm happy to be a base. You want to get rid of your proton? I'll take it. Water is accepting that proton. You should notice here, I'm writing this as H3O plus instead of writing it as H plus. Remember, that's okay. When we have H3O plus, that's just another way of representing that it was the acid that donated it, right? It's a base. So when you have a chemical that can either be an acid or a base, depending on what else it's paired with, we call that chemical amphoteric. Okay. There are other things that can do this. Water is just the most classic example. All right, I'm going to put up on the next slide some acids and bases, and I would like you to try to decide if it's an Arrhenius acid and base, BronstedLowry, or Lewis. So let's start with these two. First you have to decide, is it acid or base? And then is it Arrhenius, BronstedLowry, or Lewis? Well, I see a hydrogen here that'll come off. That's Arrhenius acid. I see a hydroxide. That's going to be an Arrhenius base. Now let's compare that to these two examples. Look at the ones that are in bold. Is the carbonate ion going to be an acid or a base? Is it Arrhenius, BronstedLowry, or Lewis? Is this one down here, C6H5OH? Is that an acid or a base? Is it Arrhenius? Is it BronstedLowry? Or is it a Lewis? If I look at my carbonate, it accepted these protons, didn't it? That makes it a BronstedLowry base. It's not donating a hydroxide, so it's not Arrhenius, but it does fit the criteria for a BronstedLowry. This behaves as basic because it's going to take these hydrogen ions out, right? It's going to accept them. Takes them out of solution and accepts them. Now this one, if we look, it gave one of its hydrogens away, didn't it? That makes it a BronstedLowry acid. All right, now for this next one, one of these is going to be an acid and one of these is going to be a base. You might notice that this is written really weird over here, OH2. That's water, isn't it? The reason they wrote it like this is because they want to show you these lone pairs, and it makes it a lot easier to draw these little, structures and stuff and show where things are moving when they write it this way. Yes, that's very strange to do it that way, but you do see that sometimes for this chapter. Which of these is the Lewis acid, and which of these is the Lewis base? Well, the Lewis acid is going to be accepting the lone pair, right? The Lewis base is going to be donating the lone pair. So when I look here, this part in red, that's the acid. This carbon was electron deficient, wasn't it? It had a spot right here where it could accept an extra lone pair. The water has all these lone pairs, it can donate it. All right, let's move on to the next concept, what we call conjugates. I think conjugates feel really confusing. People tend to get them all backwards and mixed up, and I have found a lot of luck over the years encouraging people to literally label on their paper above their chemical formulas acid, base, conjugate acid, conjugate base. So that's what I'm going to really encourage you to do, is label your chemical reaction, okay? When an acid loses its hydrogen, when that hydrogen comes off, what's left is now basic, okay? When an acid loses its proton, when the acid loses its hydrogen, the piece that's left over is a conjugate base. They're opposites, aren't they? Bases are going to gain, right? Bases turn into conjugate acids. Every one of these reactions will have an acid and a base, and a conjugate acid and a conjugate base. The trick is finding them, okay? So, here's our equation. Take a minute and look to see what's happening. Try to label our reactants. One of these is an acid and one of these is a base. Try to label which one is an acid and which one is a base. I suggest finding the acid first. Usually those are the easiest. Then what I like to do is I like to find its conjugate base. What did this turn into once the hydrogen left? Well, this turned into that. This ion is basic. It came from an acid. Now this is my base. It accepted that hydrogen. It turned into this. This is acidic. Finding your conjugates, being able to tell me what your conjugate would be, is incredibly important, because it's going to tell us how a lot of things called salts behave. If I dump a salt into water, will the water turn acidic? Will the water turn basic? Or will it stay neutral? So we use this topic of conjugates a lot in other subjects. It's huge in AP Chem. Okay. If you don't know your acids and you don't know your bases, you can't figure out what their conjugates are, can you? You gotta know your acids and bases. You should memorize the list of which ones are strong. One of your reference sheets from the very beginning of the school year lists these strong acids and strong bases. Memorize them. Anything else would be weak. Memorize your definitions of acids and bases. Arrhenius, BronstedLowry, Lewis acid. That way you can do your conjugates. That way you'll be able to do salts. Okay. Let's do some practice. Here is an equation. I would like you to find your acid and its conjugate base. I'd like you to find the base and its conjugate acid. Find the acid and then figure out what it turns into. Whatever it turns into is basic. Find your base. Whatever that turns into will be acidic. All right, well, I spot right here, HF. That's an acid, that hydrogen, right? That's going to come off. If I take off this hydrogen, what am I left with? A fluoride ion. That is a basic ion. It is the conjugate base of the acid. We're finding the things that are pairs, right? If the conjugate base were to gain a hydrogen, it would turn into that acid, right? So we're trying to see which ones go together. This is my base. If this were to gain a hydrogen, it turns into this acid that I see over here. This is the conjugate. All right, try one more. So, if you took my suggestion to find the acid first, that might have helped. If you look here, this had a hydrogen and it lost it. Most people can spot that pretty quick. Our brains have a tendency to find our acid better. This is the acid. This is what happens when it lost the hydrogen. It's the conjugate. That means water, remember, it can go either way, but this time, since this was an acid, it's going to just decide, okay, I'm happy to be the base this time. It accepted the proton. This is the conjugate acid. Sometimes people will say, are conjugates always weak, right? Are these the strong things and these the weak things? No, not at all. You can have a weak acid that turns into a strong conjugate base. You could have a strong acid that turns into a weak conjugate base. They'll always be opposites. Okay, we'll learn about that more in the salt video. So the conjugate does not by default make it weaker. It just means it's what you made once the reaction was finished. All right, switching gears a little bit, we're going to move on to the calculations. People have a tendency to like the calculations a lot better, right? We always tend to fall back on our math skills, so hopefully this will feel like a little bit of a break. pH scale. You've probably learned about this before. The pH scale measures how much of our hydrogen ions we have. How acidic is it or how basic is it? Remember, it's kind of a backwards scale. The lower the number, the more hydronium ions you have. The higher the number, the less you have. The lower the number, the more acidic. Higher numbers are more basic. Another word we use is alkaline. 7 would be neutral. Another thing to remember is that it's a logarithmic scale. So when we use our logarithms, each change in a number is a really big jump. The difference between a 2 and a 3 is a really big difference. We also have, instead of pH, we could measure pOH. Instead of measuring the hydronium ions, right, the hydrogen ions, we could measure the hydroxide. It's just backwards. They're both on a scale of 0 to 14. And you can see, well, if the pH is 0, the opposite of that would be 14. If it's 1, the opposite would be 13. The scales are flipped. Sometimes it's more convenient to measure pH, sometimes it's more convenient to measure pOH. We can go back and forth between the two. If you notice, they always add up to be what? pH plus pOH every single time is going to add up to be 14, isn't it? So we can use that to our advantage in order to manipulate our numbers. All right, I like this graphic. It looks a little bit weird at first, so let me talk you through it. The red triangle is trying to represent the amount of hydrogen ions. Down here we have a lot, up here we have a little. The blue triangle is trying to represent hydroxide ions. Up here we have a lot, down here we have a little. As you get fewer hydrogen ions, the amount of hydroxide goes up, and vice versa. If your pH is 0, you're going to have 10 to the 0 as your concentration of hydrogen. The opposite of that was 14, 10 to the minus 14. If your pH was 7, your concentration of hydrogen would be 10 to the minus 7. Well, that's right in the middle, isn't it? They're equal. So this is the same. It's kind of the equal point. And down here you'll notice if your pH is 14, well, look, it's the opposite. Okay. So how do we go from the concentration to the pH? You should notice something on this image. You should see a pattern. Let me rewrite these numbers closer together next to each other so you can maybe see the pattern a little better. Look. If my concentration is 10 to the 0, negative log of 10 to the 0 gives me the pH, which is 0. 10 to the minus 7. Well, if I take the negative log of that, my pH is 7. If I have 10 to the minus 14, negative log of that, 14. Remember that logarithms are how we solve for exponents, right? It's helping us figure out, manipulate things that have exponents in them. So you can see that pattern through the exponents. Using a pH scale and logarithms is purely for our convenience. It's not like this is some magical number, okay? It's just that people over time developed this scale because dealing with 0 to 14 is way better than dealing with crazy weird concentration numbers. So here are a bunch of calculations we can do. If you know the concentration, you can find the pH. If you know the concentration of hydroxide, you can find the pOH. If you know the pH, you can find the concentration. If you know the pOH, you can find the concentration of this. You could add these together, right? Equals 14. So if you know one of them, you could subtract and find the missing one. Another weird thing is if you multiply the concentrations together, it will equal 1 times 10 to the minus 14. So if you knew one of these concentrations, you could divide to find the other one. One of the things that's kind of interesting is that people tend to develop kind of a personal style for which order they like to manipulate these numbers in. Some people prefer to use this equation down here. Some people prefer to use this and then plug it into one of these. People will tend to manipulate slightly differently. I don't care which order you do. I don't care which combo of equations you use. We'll get the same answer. Here's a graphic that some people like. It's all the same information. It's just kind of showing you how you can get from one to the other. We call these pH squares. It kind of shows people what you can do. Here's another pH square. It's all the same. It's just representing it slightly differently. Use what is helpful to you. Okay? Sometimes people will ask about sig figs. How do we deal with sig figs for the acid-base chapter? And that's a little bit weird because sig figs, when there's logarithms involved, get strange. So technically what you would do is you would count the number of decimal places, and then you would use that number of decimals to help you do your sig figs. We won't worry too much about that. In AP Chem, you practice that a little bit more. It's not something I'm overly concerned with. All right, everybody, that was it for this video. I hope that was helpful. Bye.